So, today is the last lecture for the semester, so we should try to do something more exciting than usual. We will put all that we learned over the last couple of months to use and try to do some low-level function hooking. That is quite an interesting endeavor. So let's create a new project for that. Create new project. Hook test. The idea of function hooking is to manipulate the behavior of some existing piece of code, which you cannot change by just changing it and recompiling. So where you need to change its behavior in its binary form, basically. So for starters, let's just implement some super trivial program that doesn't do much. Let's include Windows H, and then let's show a message box. Message box v, comma L, comma L. Okay. That should be capital. Zack. And as you see, the program does what we expect. It just shows a message box. Now what we want to do is we want to change its behavior. So how do we do that? First things first, we will set here the few properties such that the compiler will not generate too much unnecessary code. So we disable this and we disable that, and safety checks as well. We should go to Linker and turn off incremental linkage. Okay, so we put a breakpoint and then we will inspect the code if it's as straightforward as we expected. So we see here that we prepare the arguments for our message box call, and then we just jump directly to the appropriate function. We can load symbols here so that we see where we are. We could load some more signals, symbols, so that we get more insight into what functions we are in. And now what we will want to do is we will want to detour this function. So we will want to have some own function that replaces the message box v. So let's create it first. So int api my message box w capital B text, and the next was caption, and the last is utype. Okay, so we have a sum function. We'll make it just return 0 for starters, and the next task will be to somehow detour the existing function to go to our function. So what we can do is we could override the beginning of this function with some own code which will do the detouring. So to do that, what we will do is first let's get the address of this function, so that we have a variable that holds this address. Void asterisk this message box v is equals message box v. So we can quickly test it that we get here the proper address. If we go to this address, we are at the beginning of our message box original message box function. So getting the address of the function to hook is quite trivial. Then for good measure, let's get the address my message box v, which will be just the address of our function. We can also see whether we are where we expect to be. So here, if we look there, we come to our function which doesn't do anything yet. So this works as expected as well. And now we will have to start our manipulations. So let's start with creating some helper structure. So to write as a binary data directly, it's helpful to have something that helps you keep track of where you are. We'll use a union. Let's call it code, and it will have a uchar pb, a word pv, a double word pd, and a int64 pq. Okay, you will see in a moment how this can be used usefully. So we initialize it with the address of what we want to overwrite, so pbyte, although here it's irrelevant which one we initialize, so just for the initialization any is good enough. Suck. Okay, and now what we'll need to do, if you remember from our last lecture where we messed around with the vtable of the application, the code this message box is pointing to is not writable. So first we will need to make it writable. We will use the virtual protect function that we used last time. Not protect virtual protect LP address is well, we can use this, doesn't matter which we use. Let's say we want 32 bytes to be unprotected. Page execute read write, and reference alt protect. Then we'll do something here, and then we will restore the previous page protection. Okay, so what we would want to do assembler wise here would be, for example, to load the address of our target function to a register and then jump to that register. So for example, move mov absolute into the register x underscore this is my message box something, and then as set the next thing we want jump to rax. That sounds easy. How do we do that? Well, we will need to find the binary representation of this assembler instructions, and we can do this using some online assembler. They are quite useful. Stupid edge. So, let me quickly find the right link. This one is good. I will post the link to the chat as well. Where's the chat? The chat is here. The chat is there. I see someone wants to ask something in the chat, so let's see. So the one of you is asking if it's allowed to use AI for the final project. I would say it's not recommended. Don't do that. Because AI, it will do something, and if you don't understand what it did, it can just break everything or do something that looks plausible which completely misbehaves. So I would say just do it on your own without using AI. I'm thinking if there is any use case where you could use AI you could use AI to write you the test cases, maybe, because they should be quite easy to understand, and in the end they must work. If they fail, then it's either your code or the test case made by the AI is buggy. But for the main class itself, I would say don't use any AI. And if you add some AI generated code, then just write a comment like AI generated code starts here, and when the code ends, then another comment AI generated code ends there. So I would say that would be the recommended approach if you want to try to use one of these new tools. I think another detail is if you are using GitHub Copilot, so this thing where you start writing a function and it suggests you a continuation. In my experience, this only works for very simple tasks, so I don't think it will be very useful for your use case. You can try it, in which case you should also mark such code blocks which have been auto-completed by AI as AI generated. Yeah. Good, let's return to our task. So let's copy our assembler code. We want x64, we don't want the comment, and of course here it will not understand what this is, so here let's just add some value. Assemble, and it spit out some code. So we can take the code as is for starters. Zack, zack, zack. And let's see what we have. So it is obvious then from here to here, it is basically the value that we passed. So the opcode itself, movefragsApps, is just those 2 bytes. And then the next jump instruction is also just 2 bytes large. So we'll now use our code helper like this. So depending on which of those I forgot here an asterisk. Depending on which of those members we use, the behavior changes. So if we use p-word, then we can write 2 bytes. And if we add ++, then it will automatically increment the pointer to the next address after the written 2 bytes. So we don't need to manually do any additional incrementations. One thing we need to not forget is that here the byte order will be swapped. So it will be B8, 48 to get 48 B8 written into the memory. And the next one will be, of course, our pointer. So this time it's 8 bytes, where we just want to write our message value, our address. Do we need to convert it? Yes, we do. Oops. Okay, and then of course our jump instruction. Again, we write a word, and here it's A0 FF. Okay, and that's already it. So in principle, that should be as simple as that to get this code be detoured into our own function. So we'll put a breakpoint here at the very end, and a breakpoint here in our function. And when we run the code, we will see that before we arrive in the last breakpoint, we will arrive in our function, and of course no message box will be shown because the invocation of the system message box this way has been suppressed. So let's run it. And as you see, we are where we wanted to be. We can also check here that we jumped from here, or rather made a call there, and then ended up in our own function. And if we then continue, we end up here. We can now put a one more breakpoint and inspect this really step by step. So here, as you see, we are preparing the arguments, we are calling it, and then here we have our move frags and jump frags, and basically just the begin of the function has been overwritten with this. So the question now would be, of course, if we would want to be able to still use the original function, how would we approach that? Well, there basically are 2 approaches which can be taken. One is very easy, but also very limited in its usefulness. When doing all these things we are doing here, one aspect that needs to be always taken into account is that there might be multiple threads running in your process, and they all might call various functions at various times during their operation. So when we are manipulating those functions, the code in memory, we can easily cause a situation where we are overwriting the code while another thread is executing the code, which would not be good, because then the other thread would start executing something inconsistent and crash. So if we have other threads which are running, then we need to take that into account and either suspend them or use some other means of synchronization such that we can be sure that they will not be using this function while they are running. That said, there is a simpler approach here, one where the function is modified when it is, for example, when the function comes from a library, then you would want to modify the function when the library is being loaded, such that your modification is in place before any other code would start using this function. In our case, this of course is not the case, but since we don't have other threads which we have started, we can be reasonably confident that nothing will use this function. Such an approach can be used for most functions as well. So if we can install our hooks in the main function before any other code is executed, then we are on the safe side, and that mostly works. Now going back to the ways how a original function can be called. One option would be of course to just make a copy of the code which we have just overwritten, and then once we arrive in our hooked function, we can then restore this code to whatever it was before, and then we could just call normally message box and it would work. But this is like a single event sort of a solution. So either we would then need to reapply the patch before we return, or we would just lose the hook, and this would be one of hook. And of course, it would also fail if multiple threads would try to call us at the same time. That's why we will not be doing this. And in principle, such an approach would require the already outlined synchronizations. The safer way of doing it, which is also much more flexible but also more complicated, is to create a so-called trampoline. So basically what we will be creating is a function which will contain whatever code we have overwritten from the original function, plus a jump instruction to go to some offset in the original function which is no longer modified. So if we quickly rerun our example, and here go into the code, we see we have modified like until here, so we would somewhere here want to jump after we have executed whatever code we have backed up from there. So to do that, let's first create a so to do that, first we will need a type definition for our trampoline function. So def type def int, we can copy most from here, and we will call this pMessageBox. It's basically just, as you see, a copy of def of this. I'm missing an asterisk. Suck. And now we can define a variable of this type, tram, which will be callable like a function. So once we are done with it, for now we just set it to null. But once we are done crafting it, we could call it here with all those arguments just fine. That's how it will work. Now we just need to get it to work. So first things first, we will need some memory for our trampoline function. And we should of course create our trampoline before we start modifying our code, since we will need the original code to be intact for this to work. So let's 64. Let's allocate some memory. Tram. Nobody else. This variable is equals. Yeah. So there are a few considerations when allocating the memory for our trampoline function. For example, we would like the memory which we will be allocating to be rather close to the place of the code which we are modifying. So to achieve this, what we can do is we can start a loop. Stern, address Stern, and we started the address of our original function. Zack. Then we will repeat as long as our trampoline is null, and if we need another iteration, we'll just add. Oops, this will be next. One page. So we just go to the next page, and so on and so on and so on. And now we will be using the virtual alloc to allocate. To try to allocate. We need the right type. Zack. Okay, and virtual alloc allocates memory, and we can provide to it optionally the address of the memory where we want the memory to be allocated. And if we provide an address which is already in use, then it will just fail and return null. So we just start with our original message box, which will most definitely fail, but I mean, we could in principle optimize it by just already adding here some offset. Let's say 8 pages should be enough. Right. And now we specify how we want the memory to be configured. So mem want it to be committed, and mem and reserved. Comma, and then we want, of course, the same protection which we would use here. Page execute read write. It's not safe, but it's what is useful for us. And now this code will be executed a few times until we find a region in the memory space of our process which is as close to our original function, but yet not used by anything else, and then we will get our space allocated there. In principle, we could implement this search in both directions, so not just search in the plus, but also in the minus direction from where system message box resides. But for simplicity, let's just go one direction. Okay, so before we continue, let's quickly disable this code and grab the original code of our message box v function. So again, we here enter it, and now let's copy this much of it. It should be good enough. Zack. Okay, so we have. Let's write the code here. Wait, it's not. I don't like this. Let's switch this. We don't want to see the addresses, but we want to see the code bytes. Yeah, that's more useful. Zack. Okay. So this is the code that will be overwritten. So now let's find a good place to jump into. We know that our code here is, how much is it? 12 bytes long. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 12 is somewhere inside this compare instruction. So we will just go until the end of this. This should be, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14. So that sounds as good as anything. So let's write it down. 64 tram target. oops, plus 13. So this will be the address to which we can jump. This will be this jump equals instruction, and we can be sure that only how much about this much, is it 12? Yeah, it's 12. About this much code will be overwritten. You might also notice that if something would be executing that code or so, then here, starting from here on, we would even get an inconsistent compiler output. So what we could do in principle here to make debugging easier, if we know the offset of the next valid opcode, we can pad out the rest of the code with null x90, I think. But that's not a word, that's a byte. We want to fill 2 bytes with null 90, and this should be the nop instruction. Yeah, nop means just no operation, so it just does not do anything. What we also could do is int3, which would be cc, I think. Yeah, that would cause a exception. So what we prefer is up to us. We can, let's go with cc. So in this case, this would be then actually can we? Yeah, we can use both. Whatever we prefer. Let's go. Let's make it like this, and we demonstrate everything we can. So we just add those two to our printout. Oops. Right, and then 90 on CC. Okay. This is not needed for proper operation, but if you would be reviewing the code with a disassembler, the fact that you kind of get some end part of another opcode standing there would throw the disassembler, of course. We can actually view this even. I will comment this quickly out. Run it, then we will see how this works. No, sorry, I forgot the breakpoint. We need a breakpoint here. Zack. And now, if you see here on this code, and compared with what we have here, this JE and move and so on is fine, but here it thinks there is an add instruction which does something, but it's just the remainder of this thing. And in principle, depending on what was there before, it might even break the disassembly of the following instructions. So if we nop out or cc the code which we are overwriting, then we can be sure that the decompiler, when in use, will show the code properly. So in this case, we see that we have the nop, we have the int, and then it continues with the next instruction as it should be. So let's add a line here so that we have an indication to where we are modifying the code. Good, so far so good. So the next thing which we need for our trampoline is to know the no, that's for later. Let's just start writing the trampoline, and then we will do the other thing. So code .pb is equals unsigned char asterisk trampoline. Zack. Okay. So asterisk code .p double word plus is equals. So let's start with the first thing, this sub that we have here. So this is then a null x 38 ec 8348. So this is our sub comment sub something. Let's maybe tab this a bit further. Okay. next instruction. Code. So the next one is 3 characters long, which is not great because we don't have a type that will be 3 characters long. We could use 2 approaches: either use a 2 and a 1, or just use 3 single bytes. So I think for simplicity, for consistency, let's go with 3 single bytes: 0x 45 45 33 and db. This will be our XOR instruction. Okay, and now we only need to add this compare instruction, which is a bit long. So in this case, we could use a combined approach. So we use one approach to write 3 thingies, and then we will use a D double quote to write the final offset. So let's see what. Let's first copy this here, and then let's see what bytes we need to put there. So 44 39 1 D. Okay, now 0 0 0 3. I did it correct. Yeah, 0 0 0 0 3 F0 and 4A, and of course 0x in the beginning. That sounds about right. Okay, semicolon. Is that right? Let's think about it. It will change the order, yeah, so it should be fine. I mean, we can kill the leading zeros. That should be okay. And now, after this has been executed, the last thing to do will be to jump to the original code. So we will grab the code we have already written, because we basically want to do the same thing here. Just here we are jumping to the trampoline target, and we have not added any comments, so we could maybe add those. And since we are not overwriting any other code, we don't need to pad or do anything, we just put those things here. Okay, and that should be it. Our origin. Let's add some comments. Here, create trampoline. Create trampoline. Now the code as is will fail. You will see it in a moment. It should crash, and then we will think about why. Okay, we don't need the breakpoint, and voila, it crashed. So the problem we are expecting. So first of all, does anyone have an idea why it is crashing? What we did wrong? Okay, if no one says anything, the problem is that this compare instruction here, it takes a pointer, and the pointer, the way it is written in here, can see if it will be more insightful if we disassemble it with this tool. And as you see here, it is kind of much more insightful than what the other disassembler gave us. So in principle we could feed it just the whole code here and see what it will do out of it, and then we will discuss the results. Okay, zack. Let's copy this, put it here as well. And here we are jumping. So as you see here, what actually is written in this opcode is to take the value, a double word value at this memory address, and compare it with the R11 register. And the way it tells it to take these values, it takes the instruction pointer, so the position in the code where we are right now, and adds to it a number. And that is where the value in memory is expected to be. Now, since we have moved this code somewhere else, or copied it basically, this value is not longer correct. So basically what happens is this value is now pointing just into some invalid memory. So to fix this, what we need to do is we need to calculate the displacement of the trampoline. So let's do that. Int 64 trampoline displacement is equals unsigned char trampoline message box minus uchar system message box. So this value here will be representative of the difference in position of between where we are supposed to be and where we really are. So now here where we are using specifying this value, so you might recognize it from here. It's exactly this value. We will just subtract from it our displacement, and this way the relative value should again become correct. And as you can also see, the reason why we needed to allocate the code as close to our original code as possible is hidden here, because this operation here takes as a offset only a double word value, but we have a whole 64-bit, so quad word address space. So if we would have allocated our code just randomly somewhere, it is very likely that it would be outside the plus minus 2 GB window of what can be addressed using this addressing mode. So since we have our displacement minimized, we can put a breakpoint here to see how big it is in fact. So as we see, our displacement is only, well, it's not super small, but it's also not like extremely large. So let's disable Hexview. Let's see how much this is. That is yeah, we are about a megabyte and something displaced, so that is not very far. Right, and we could run our code, and then it should no longer crash. So let's try this. Yep, and as you see, it showed us a message box as if nothing would have happened. So you might say that is a bit anticlimactic, so we just did a lot of to arrive at the same result, but now the fun part starts. We can do whatever we want here, and it will be done before this is executed. Or we could of course execute this first and then do something with the result. So we are quite flexible in what we are what we want to do. So for example, here we could what could we do? We could modify the message. So we could say lp text is equals lpem. Let's okay, that's not the way to do it, because this is a const. So let's just actually it doesn't matter. We can just say that we expect the arguments here to be writable. lp char lp. It's a char. We don't want char. It should be vchar lp cv str. Yeah, and we have a bug here as well that we used the. Wait, why is this now complaining? Oh, no, it's not complaining. Yeah, it's fine. It's not complaining here. Why? Yeah. We can hack a bit since we are hacking anyway, so it doesn't need to be perfect code. And as you see, now we have manipulated the message box. And now, of course, no matter what the application tries to show, each time it will just display our BAM hacked message. Zack, zack. So this already shows you to some extent the ability of this mechanism. We could for example here do something more useful. So let's say if message box mb yes no or okay cancel. Okay, cancel is ungleich id okay. Then oops. Here fail. -1 and else success. So basically what we are doing is we are showing a message box, and if you press OK then you get success, and if you press something else, in this case cancel or close the window, you will get fail or failure. So, and maybe here we could actually have a proper prompt. Question mark. Yeah. So let's first maybe turn off our hook. We can quickly see the behavior of application. So, do you want the application to fail? Okay. Oh wait, the question is wrong. It will be an MBS no. And if this is yes, then fail. ID yes. Now the question makes sense. Do you want the application to fail? No. Success. Zack. This one again. Do you want the application to fail? Yes. Failure. So we can copy the prompt, or we can be just very lazy and only check the. Let's not be lazy. Let's do it the full way. So first of all, we will re-enable our hook code. And now we will do something. So here in this case we want to put the compare string text with this prompt. So if this is equals 0, so if it's the same, then let's return ID no. So kind of we pre-answer the question so that the user just won't see the question at all. We run it and bam, success. So we have silenced one of the message boxes while allowing any other message box with any other content to work normally. And no matter how many times the function will be invoked, each time the application wants to ask the user whether it should fail, the system will automatically answer for the user no, continue. This of course is at this level a bit of a basic demonstration, but I think it illustrates nicely enough the core principles. So obviously messing here with our own functions is only of limited use. It would be of course of more use if you would have some library that needs some modifications. So then, I mean, in principle here we have also modified the user32 library of Windows in memory, so only for our process, not for any other. But generally speaking, you might have some library that for some reason needs some sort of modification. A real life example would be, assume you have a library to communicate with some hardware, and this library is very old and it only accepts COM port numbers 0 through 8. Sorry, 1 through 8, there is a COM 0, and that's it. But on a modern system you can have a few USB hubs with a few dozen COM port to USB adapters, so your COM port might be number 20. And while you could of course try to just change the port number so that it fits within the range that works for you, if you would have more of those devices, then you would never have enough ports in the range 1 to 8 to connect all of them. So in such a case, what you could do is you could just feed to the library always COM1, and then when the library tries to open the COM port using the ntcreate file or ntopen file system call, then you would modify the call to not opencom1 but opencom22 or whatever you want. So that would be one example what you could do if you are in control of the application, and the only thing which you need is to modify some library. So are there any questions? Was it clear what we done here? Okay, no questions, so I guess it was clear enough. So let's see where we can continue from here. So the obvious next interesting, useful thing to do would be to try to modify an application which we don't have full control over. So let's create it. Add a new project. Let's call it target app, and create. And the target app will be just doing the same what we did here. It will display the message box, and depending on what the user says, it will either succeed or it will fail. So this is not very exciting for yet, but let's just leave it. Let's just quickly compile it. I will not change the project settings here to be more transparent, because I think this won't be necessary. So let's think about how we would modify this application. So one way we can modify it would be to create a so-called loader, so a process which you start, which then starts the other application in a suspended state, and then modifies the suspended application such that it will do something before it starts executing its own code. And this something will be to load our own code first. It will install some hooks, and only then the application's code will start to be executed. So let's add another project. Let's call it uploader. Create. And for good measure, we'll need one more project. As I said, the loader will load our code into the other application, and while there are many ways how this can be done, one of the more convenient ways is to just create our own library and then force load this library into the target project, into the target process by the loader. So this is like the simplest approach. So let's create a new project. Just that this time we need a DLL. And we'll call it inject DLL or hook DLL, hacker DLL. That sounds nice. Let's call it hacker DLL. So as you see here, the project for the DLL is also quite, so it created a few more files, but basically most of them don't do much. We have here the sample function which one could use, which we actually won't need. We also created for us here a sample class, but we really don't care for those things yet. We can just exclude them from the build for now. The only thing we are interested in is where was it? DLL main. Here our DLL main entry point. This code will be it's like the main function of an exe, just that it is called more than once. While the main entry point of an executable file is only called when the file gets started, and that's it. For DLL, this DLL main is called for all those different reasons. So attach process means it is called with this argument when it first gets loaded into the process, and then for every thread inside the process which gets created, it will get this thread attach event. And then of course when a thread terminates, it will get this thread detach, and when the library would be unloaded from the process, it would get this DLL process detach. For us, for our use case, we are only interested here in the first case, so we can add a function void DLL DLL entry and call it from our DLL main, and we ignore the other cases. But before we can start writing our DLL, let's see how we write our simple, or maybe not so simple, but our nice DLL loader. So first things first, we will need to know where we are ourselves. So we assume, by the way, I will here quickly build the project, and then we will see what we got as an output. Zack. So as you see, we have here by type all our binary files in the same directory. In principle, the loader could be made such that it takes a command line argument which points it to which process to start, and then which tells it which DLL to load, but we want to keep things simple. So here we will just find out our own path, and then once we have found out our own path, then we will look into how to start the other process. So char LDR path, so this will be our path, max path. This is the definition for path length on Windows. It is a limitation for the standard use of the Windows API, but you can also, using special syntax, alleviate this path length limitation and use paths up to, what was it, 65,000 characters in length, which doesn't sound reasonable, but in some cases might be useful, and it's good to know that if you need that, there are ways to use it. But for pretty much any normal use case, the normal path length limitation is good enough, and here especially when working with just C and not C++, it's nice if we can just define something that's not too large, and we know that it should fit whatever we get. So get talking about getting, we will be using the get module file name w, and if we specify null as the module, then we will get the path to the main executable. Otherwise, we could provide here the handle to a loaded DLL, and then we will get we would get the file name of the DLL. One thing to take into account here, this gives us the whole path, so it is it contains also the file name, but we don't want the file name. So what we will do is we will use the vice wcsr chr function, right, which takes a string, and then it searches for the last occurrence of a specified character. So we just look for the last backslash, then we move one further, and then we just at this point set the string to be null. So just terminate our string early, and this will give us the path. That's the wrong process. Let's set here uploader, set as data project, run, and voila, in our thing we have the path with the last backslash, but without the file name. So now we can create another path based on this path. Using std string would make things easier, but well, wcs cpys wcs cpys destination is our app, comma, the max length is max path, comma, and we copy what we already have. We are not modifying the existing thing because we need that for the DLL file name as well. So what the next, now we add just the file name, vcs cat s. So cat concatenates vcs cat s, it should be fine. Yeah, this concatenates two strings, and here we can provide what was the name, target app, and this will give us the right string. Okay, so now we know what we want to start. So now let's see how we start a process on Windows. We can do it using a few different API calls, but the one which is most useful for us is the create process w. It takes a application name, so here the app path, or maybe I should call application path, comma. Then we can provide a command line, in this case null, because we don't want any. Then we can provide security attributes. We don't want that, and for the thread, we don't want that either. Don't want it to inherit any handles. And now it asks us for the creation flags. The creation flags specify a few properties how the new process will be created, and the one that is relevant for us is the create suspended. This means that the process will be created, but it will not start executing any code yet, so we can modify it before we resume it. Okay, environment null, directory null. So for the environment and for the working directory, if we just specify null, it will just take the defaults. And now there are the last two parameters, startup info and process information. For the startup info we don't care, but we will need the process information. So let's get create here those two structures, SE 0, and this one just pass as reference, and here the more important one, process information PE is equal, so we initialize it with zeros, reference PE. We could check whether it returns an error or not, but we don't care for that. And for the process to start executing, we need to resume the one thread it was created with, and its handle we can get here from the process infrastructure. So we haven't done any injection yet, we just will be doing injection here. We now just start it and see whether it works as expected. So as you see, the thing finished, and then the other, so this one kind of is already running, while this thing here is still asking us what we want to do. And I think there is one thing that will be useful. Okay, let's not install it. Okay, we can put a breakpoint here, and we could put a breakpoint there. Run it again, and when we go to our target tab, you see the breakpoint is like this empty circle, because the debugger is not attached to the new process, even though it already has been created. So we can go to debug, attach to process, target, and we can attach to it. And then if we press play, where we end up in a breakpoint inside the thing, but then, so by pressing play we have executed this line and resumed the other code. We ended up there in a breakpoint. Here we get into the other breakpoint, and if we continue this, we then end up in our new child process in the breakpoint that is actually interesting for us. So this much just to the debugging. And now what we will need is we will need to somehow inject our DLL, and there are a few ways how this can be done. Let's start with the simplest one, which is just to use a create remote thread. So void inject comma age handle age process comma then the DLL path, and of course we'll need the DLL path. So let's quickly copy this code block here, and I already had a name for our DLL, hacker DLL. Oh, and let's put a breakpoint here as well, so that we are already ready. Oops. DLL, and then we will call our code injection. We need a handle to the process, which again can get from here, and then we can add the DLL path. And just for good measure, when after we use create process, we should close the handles that it opened. So on the thread and on the process, both threads, both handles should be closed. Of course, since the process here terminates instantly, it's not really relevant. But if you would have a process that runs all the time and then injects things into other processes all the time, then you would not want it to crash at some point because it is using up too much resources. So always keep in mind to free those resources after they are not longer needed. So looking into our create remote thread injection function, let's see how this would work. So there is a function in Windows called create remote thread, and what it does is it creates a thread in another process, and this already sounds quite useful. So we have to specify in which process, then we have to specify something, so this can be null, this can be null as well. Then we will need to specify the startup address, so the address of some code within the other process which we want to have the thread executing. And this is already one of the more problematic aspects, because how do we know which code in the other process to execute? And one approach here is that we take just a function which we know where it should be, and for example this could be void asterisk library w. So we just get the address of the load library w function, which is part of the I think 132 DLL. And what it does is, as we can see here, it just loads. It takes as one argument a pointer to a DLL, and it loads it. And the way on Windows DLLs, system DLLs are loaded, or well, any DLLs are loaded, is that when two processes load the same DLL, Windows tries to minimize the amount of memory used. So if one process already had the DLL loaded, and then another process starts and wants the same DLL, then it will take the memory of the other process, which as such should in its entirety be for this DLL, it should be read-only, and then it will share this memory amongst both processes. And in the moment where one of those two processes would try to modify something in the DLL, as we did with the user32 DLL with the message box W function, this causes an exception, but one that the operating system is handling and then resuming execution. So what it does is it implements a copy on write mechanism. As you might remember, the idea of copy on write already from some of the classes we have implemented, it's that you have something shared, and as soon as someone tries to change something, that someone will get its own exclusive copy, which they can then modify. And in this case, this is not done like on the whole DLL, but it's really done on a page-by-page basis. So if you want to modify one function, only this one page is copied. So at this point, our test hook has like the whole user32 DLL, and only one of the pages is not from the original DLL, but I mean, of course, it could be like 2 pages if you were directly on the boundary and overwrote 2 pages. But generally, it will be just 1 page that gets modified. But the important thing to note here is that as long as there are no modifications to the DLLs, all the DLLs would physically reside in the same memory. And since usually DLLs, or well, any code, is not entirely position independent, so there are things in the DLL like strings or other resources or jump addresses which can be position specific, so not always just relative to your instruction pointer, but for example absolute values or something like that. This means that if the DLL is loaded to some special address and it is to be shared amongst 2 or more processes, then it must have the very same address in all of those processes. If it would have a different address, then some of the position dependent code in the DLL would be broken. And you might also wonder at this point is when loading the DLL in memory, what would happen if the default memory location where the DLL would want to reside would already have been used by something else? And the answer is pretty simple. In this case, the DLL is just loaded in a different place, but then the DLL loader has to go through the whole DLL and modify all the offsets which are position dependent. There are actually special tables within the DLL image which contain a list of all this position dependent code. It's called the fixup list, and the loader, if it loads the DLL not to its default base address, which by the way on modern systems is always the case, even if the default base address would be free, the loader tries to put it just somewhere randomly in memory, such that if you have different computers somewhere, not all of them will use the same addresses, so that if an attacker is writing some code that would target a certain address, for each time you reboot your computer, the addresses to target would be different. It's called address space layout randomization, and it's quite a useful mitigation mechanism. So basically the DLL gets loaded somewhere, it gets patched, and then from wherever it was loaded, it gets shared amongst other processes, but without being remodified and repatched and recopied. If like the last instance of the DLL would be unloaded and then it would be loaded again, it might end up in a different memory location. But here, since we are modifying system libraries, they will be loaded by something all the time. So effectively, we can work around the need to find out where the address in the new process might reside. We just take our own address and then we just rely on the fact that in the other process it should be the very same. Of course, this gets much more complicated if we would be in a situation where we would, for example, be ourselves a 64-bit process and our target would be a 32-bit process. Then we would, of course, not be able to do such a trick. There are API calls that allows you to enumerate loaded modules by a process and enumerate memory ranges. So there are ways how one can find out addresses within other processes if one doesn't have the address available oneself. But that complicates things, so we will not be doing that. Okay, so we have our address for our load library, and of course the next argument for our create remote thread function will be a parameter, which is the first argument which will be passed to the start routine. So when we review it, the startup routine has one parameter, which is nice because our create library function also has only one parameter. So now we just need to find a way how to fill this parameter, and we will do it by allocating memory inside the other process. So with asterisk ADR for address, use virtual alloc x this time, and then we just specify the handle to the other process, comma, the address null. It will just pick, if we specify as address null, then it will just pick some random address and give it to us, which is fine. Size should be max path. Allocation type mem and page read write. So it should be readable and writable. Okay, so we have an address in the other process, and then we can use write process memory to write into the memory space of a different process, which obviously sounds like a huge security violation, which it kind of is. But the way this works in reality is that you need to have a handle on the process, so this H process, and that is where the security mechanisms will usually kick in. So let me just quickly finish this, and then we get here, this can be null. So it would tell us how much it wrote, so in case it would fail to write, it might have been able to write something. But returning to the security aspects. When we are creating a process, then we obviously are in full control of our child process. So here we get a handle which can do pretty much anything. And obviously manipulating child processes is just fine. It becomes more of a security concern if you would want to open a handle on some process which has been created in the system by some other process which you might not have the right to modify. And for that there is the open process function, which will actually do a lot of access checks. So it will check whether you have permissions to modify the other process, and only then you will get a handle which allows for writing. So the way this works is when you open an object on Windows, any object that is securable, like a file or a process or some synchronization objects, then you have to specify which access rights you want, and the kernel checks whether the access control lists for this object allow you, based on your user token, to access those, to get those access rights. And if you can also like ask the kernel to give me the most rights you can, which then it will just see what would be permissible and then give you those rights. And those rights can be either reading or writing, and of course there are like multiple levels. So for files like reading file content, writing file content, reading file attributes, writing file attributes, deleting file, synchronization, and a few others. So usually you can get the read-only set of permissions on most of the processes which belong to your user session. You cannot get a readable handle to a process that belongs to another user, because that would also be, of course, a security problem. If someone opens his super secret Word file and you then can read his memory, then they could access his secrets. So obviously this wouldn't work. So you only get usually to read the memory of the processes which belong to you. And with regard to writing, this is even more restricted. So usually when you are running as a normal user, you can start some processes, for example, as administrator, and then you would not be able to access those processes from a normal user process. And of course, processes that run within the system account are as well protected. So to access those, you need to have administrator permissions usually. Okay, so this much was to this small detour. So let's see. So we have our memory, we have written to it. We have our address, we have called it. Right, we need to specify the address. Then creation flags, let's say 0. We want the thread to run instantly, and here we could get the thread ID, but we don't care for it. But what we care for is the handle to the thread which has been created. And I think what we could do, so we could wait for it. Wait for a single object, comma, we wait for it for a second, and then we continue. So at this point the thread should be done, and then the rest of the code will start being executed. Right, so let's put a breakpoint here and run it. Zack. Okay. Then, so we have our process, so we need to attach to it. Okay. Then we continue. Then we get into some internal breakpoint. Don't care. And then here we are in our in our entry point. And when we review here, we see that from this hacker DLL, we really have don't see the process here. Can we see that somehow? Debug window threads. Come on, Zack. Okay. So we have here the two processes which we are connected to. One is the uploader, and the other one here is our target app. It doesn't show us the name of the. It only shows us the process ID. It doesn't show us the image name. But if we continue execution, we'll end up in the main thread here, and then we see that this really is the other process where we ended up. So for now, as you see, we have not done anything yet. So the thing will just show us the message box. So now what we need to do is we need to copy the code from our hook test sample, where was it, here, into our DLL. So that is easy enough. I can DLL main here. Until there. Okay, so let's run it. And since we are confident in our process, we will not be single stepping through this. We'll just continue. It didn't work. It should work. let's see what went wrong here. We have this. Let's put a breakpoint there, debug. Okay, let's run it. Now we will attach to process. To see the order of operations. Okay, it is not loading our DLL. That let's see why. First of all, let's add a short delay here. Just to ensure that this is not the thing that's failing. It's really failing. So something is wrong with our injection code. Let's see what's wrong. Let's put a breakpoint here and see whether we actually create that thread successfully. That should be right. Threadpods memory, max path null. Right. Don't have enough memory, possibly. That was one bug. So of course max path is the count of characters, but our characters are bigger than 1 byte, so we need to multiply it. That was successful. Still not working. We have the address, we have the path. Let's see whether the path is right. That might also be a bug. Path. Hacker DLL. Oh, I know why. Very stupid mistake. The thing is, we have not configured our project dependencies yet. So it didn't rebuild the DLL. It still was loading the DLL, which did not contain. So if we now click on this and build, as you see, it doesn't do anything. But if we click now on properties, and now we will say uploader, project dependencies, DLL loader is depending on the DLL. And now we say build on this. You see, it first built the DLL before it said that the other project is up to date, and now it should work. Play. You see, it just tells us success. It does not. It does not show us the other message box, which would prompt us to do something. So this would be one way of loading a DLL into another process. As mentioned, it is a very simple way. It is quite common, so like when you would Google for how to do DLL injection, it would probably be one of the very first results which you would get. And it's a good method, assuming you have the necessary information, like the address of the load library function. But of course there are other ways which we can use, so we can take a look now into another method of achieving the same goal. So the next approach is we could try to queue a asynchronous procedure call, although this is a more elaborate approach. I think it would be nice to demonstrate since it does not require too much code. So let's try it. Void inject queue user APC, and oh, it didn't type again. capital. Okay, this thing needs the process handle. It needs the DLL path. And what we would also need will be a thread from within the one thread from within that we can hijack. So let's add here handle a thread. Okay, so at the beginning we do the same thing. We prepare some memory with our DLL. So here we will still want to use the load library function, but we could also use a different method here just for demonstration purposes how to obtain this address. So instead of just using it directly, we can use get procedure address, get module handle, yeah, L and comma library v and no L. Okay, so this method also works by using our own address, but in principle it's slightly more robust because you could in principle here, instead of get module handle, use load library again and then load some other DLL which you know which you would then assume would get the same address. So you could for this, of course, you would need to be able to load the DLL. So it doesn't work if you have a 32-bit process trying to inject a 64-bit process or vice versa. But if you have the same bitness of processes, then you could use these methods to get the address as well. Okay, and then let's use the function. Q with the APC. Right, PAPC function load library, comma long ptr, and then the address. So write it there, and that should be it. Let's try it. I will put a breakpoint here. Wait, it's complaining about something. Right, I forgot the thread handle. We of course need to specify the thread handle as well. Let's see if this will work. The advantage of this approach is that it does not create an extra thread, although the other thread only lives for a very short while, so this would not really be that much of a limitation. We forgot to switch to the other function. Right, and here we forgot to add the thread argument. Suck. Right-yo. It said okay, that sounds promising. And as you see, success. It also worked. There is no such a clear-cut distinction between those two functions. I would find this approach to be more robust, because when you are creating another thread and running it in the other process, depending on some scenarios, you might find yourself in a situation where you cannot effectively keep the other thread suspended when you have resumed your own thread. So there might be some race condition, but doing this will force the execution of our load library to be done within the main thread of the application. So we can quickly try to inspect that in detail. So we have here our where we had it code, right? So debug attach to process. We have a couple not terminated target applications. Let's quickly take care of that. Okay. Debug attach to process. Target app attach. Right, now we run. We again hit some internal breakpoint, and then we don't care for this breakpoint. We don't care for this breakpoint either. And now we are inside our DLL, and as you see, here now we are in the main thread. So if we go to call stack, we see that the thread started its existence somewhere in the NTDLL, then it did some things, and when we then later go to our main target tab, we modify target tab, so the debug informations are no longer valid. Let's quickly fix this as well. We can here to properties and set here and set our uploader to be dependent also on the target application, so that it also has to be up to date, right? We can remove this weight here, I think. Okay, so again, debug attach to process, attach, run, continue. We are here in the entry point, and rest up. This breakpoint also ready, and if we click on it, we will then arrive in the same main thread in this entry point. Okay, so as said, I would personally prefer this queue user APC approach, simply because it avoids the risk of having two threads run in parallel, and it gives us really nice control. There's maybe one more thing we should maybe again take a look, which I skipped before. Again, if we attach this, and then we continue and continue, right? It might be interesting to see from where this DLL is actually invoked. So here we should load symbols. Okay, so you see the rod library xv, which is basically what we are then calling, is here called, and then we have, and it calls a load DLL from NTDLL, which then does all the stuff until it's done with loading, and then it invokes our entry point. And this code here is then invoked from the NTDLL function RTL dispatch APC calls. So such an APC call, in the way it is designed, so APC stands for asynchronous procedure call, and the way it is designed, it cannot interrupt the execution of a running thread arbitrarily. So the thread needs to be in a alertable wait state for an asynchronous procedure call to be able to be executed. So if you would have some application which runs and does things, if it doesn't call the right functions, you might not be able to get your own code in by using this method. When you're creating an application from scratch, as you see here, the NTDLL always calls this special dispatch function to execute all waiting asynchronous procedure calls. So it will always work on a process which you are just created and which will only start running once you resume it. But if you would want to do something with a normally running process, it might be that it will take for it some time to get to such a alertable wait state. for example, you saw me before adding a short delay, this sleep, which just takes milliseconds, and this one is not alertable. There's a sleep X which is alertable, so, and it is a special parameter. So if you would have some code where you just make a sleep and make let's say you make a loop which makes sleep in short intervals, and then does something other, and then and so on and so on. If you don't use the sleep X with the alertable flag set to true, the normal sleep will not be able to be interrupted by such a asynchronous procedure call. So it is not as versatile, one could say, than the create thread approach, since with this create thread approach you can really hijack any application already running, no matter in which state it is, unless it's already terminated or in process of being terminated. So that's that. And since we still have some time, I think I can show you yet another way how one could intercept the execution of a process which is in the process of being created, which is called thread hijacking, and it's a little bit more elaborate. So I think that might be interesting. So let's do it. Uploader. So again, we need the same parameters here. Hijack thread. Okay, so okay. So first of all, we need to get the thread context. CTX and CTX. What was it? Context flag is equals context this control. Oops. So the way this set of functions works is that based on the context flags parameter, you can specify which parts of the thread context you want to get or set. So get thread context, and then we pass the thread handler and a pointer to our context structure, and it will only get the fields set which are here set as relevant. You can, like, control is everything that's control flow related, so instruction pointer and so on. Integer, that will be like the standard registers which you already learned. Segments, these are registers which usually you cannot control from user mode, so we don't care about it. Floating point are the other registers for the floating point numbers. Debug registers are also more hardware specific, so they should not be something that you can set without the kernel's permissions. But here, the simple thing what we want to do is just ctx punkt ep, and we will just set the instruction pointer to be something different. And so we will set this to something, but for now let's set it to 0, and then we just need to set the context. Obviously setting it to 0 will just make the application crash, so we would not want to do it in production. But here in our own custom use case, we will create a function which will give us the right addresses. So void asterisk right shellcode. This thing takes process, comma, it takes the return address, so where we want to go back once we are done with what I want to do. And then of course, since the shellcode will load a DLL, we at DLL. So write shellcode here, zack, process. The return address will be just the instruction pointer. And the DLL path will just pass to our new function. Okay. And now, first we will need to create some memory where we can store our shellcode. So, and then of course we will also need to create some memory for the DLL. So let's start with that. As usual. Yep. Okay. Now let's first create some buffer for our shellcode. My code. Let's say it's 1 page or 1000, not even 1 page, just 1000 bytes long. Let's initialize it to 0. Okay, then we will need to create the actual shellcode add memory in the target process shellcode. H process, here we will, oops, just size of my code, and commit, read, write, execute, read, write. Very important, without execution it will not work. We will need some DLL loading address, so this time let's try the LDR load DLL. And here we'll use this approach, but this time we want the ntdll.dll, and here LDR load DLL. So we will now be using a function in the ntdll instead of the load library from the kernel32DLL. The reason why with the above approaches we are using always the load library W or load library A is that it only takes one argument, and this one argument we can pass to it in both scenarios, using the remote the create remote thread as well as using the asynchronous procedure call. With with loader load library from the ntdll, this one takes 4 arguments, so we cannot use this approach. It is we would not be able to set those 4 arguments, but using a shellcode approach, as we are doing right now, we can in fact set any arguments we want. We could even write a very complex code that loads calls multiple functions and does a lot of things. So depending on what our goal is, this would be a very good approach to have a robust implementation. Okay, we will steal something from here. Our code writer gadget, because it's super useful. Where will we load it? Here. Right, code writer gadget, code dot pb is equals my code. Okay, what else do we need? We will need some offsets, so write them down. Hash define ret offset, return offset. So we will have to pass a few things to the shellcode, which will be passing as part of the shellcode, and we will just write them like in different offsets of the shellcode. So in this case, at offset 0 we will have the return address, so this is this one. Then hash define LLD offset 8 will be the offset where our load library DLL lives. Then hash define path offset where our path lives, and do we need anything else? That might be it. let's see. Let's see how far we go. If this is all we need. So we have created our we have initialized our shellcode thingy. We will now need another helper thing, hash define base, a macro which will give us always the right offset relatively to the instruction pointer. So this thing, how does it work? Code dot pp minus my code. So this gives us the relative position. We negate that. We need a we need a negative value. Right, and then from this we have to subtract size of double word. So the size of what we'll be writing, because once we are done writing, it will be advanced even more. So we need to take this into account before we write. And here are the comment. Gives the position from the current instruction pointer. And what's also helpful is to write your offsets down so that we know where we are. Then code dot pqv plus plus is equals in64 red adder. Okay, then 8. This was the load library. Okay, next one. Path length, path size. Right, we need the path to be as provided as a not as a C string, but as a what's its name, Unicode string. So Unicode string. Isn't that defined anywhere? Should be defined somewhere. So as you see, the way it's defined is we have a short which specifies the length of valid data, then the total length of the buffer. Then here is a for unused bytes, since as you remember the structures get aligned. And then we have a pointer to the actual buffer. So we need to create such a thingy ourselves, because that's the format the LoadDLL loader expects. So this, as you see, complicates things. So let's see what we'll have. Size t path len is equals bcs len dll path size of char t. Right, then we need the total size. Let's go t path size is equals max path. Yeah, okay, we should have all we need. Yes, so zack 16. Okay, there we are. Let's go. Address code .p word, so that's 16-bit plus plus is equals path len path. Oops, that's the wrong one. Path size. Now pd plus plus is equals 0. That's the padding. And pq plus plus, that will be the address. This one. Wait, was this was defined as void, so we need to cast it. In 64. Zack. Good. And now 32. Let's give it some more room. Right, we will need one more offset. We'll offset 32. So maybe to understand this, let's quickly review how this function actually works. It's a undocumented function, so that looks like a reasonable source. No, it's just a function. Ah, come on. Microsoft Bing sucks. And this gives me the first result is the right one. The undocumented NT-internals page. So this takes here a path to a file, actually as a PU-char, but it says it's optional and we will not be using this argument. So for us it will be 0. A flags will be 0 as well. Per Unicode string, that will be the Unicode string we just constructed, and then once it loaded the DLL, it will return the handle to this DLL as this module handle. So we will need some writable memory of the size of uint pointer, which we can pass to this load DLL function, so that it will be able to successfully return a handle. Even though we don't care for the value of the handle, we need to provide this memory so that it can write it to there. Otherwise, it would crash, I guess. So right, so we have created here. So let's just add here a 0. This we will be overwriting later on. Good. So this gives us at offset 30, and we should remember this position because everything we wrote first is like data and the scratch memory space. By the way, we could in principle have combined those two memory allocations into one and then just write one bigger part, but for now let's just continue this way to have more symmetry between the different approaches. So here what we will do is we'll byte asterisk my entry. Remember this offset is equals code.pb, and then we return this at the end. So here when we set the instruction pointer, we'll set it to the next line, which we'll just write in a second. So since we might want to enter the shellcode with a debugger, let's add a debug break. Oops, it's not typing. Debug breakpoint, and the debug breakpoint, you might already remember how it looks. It is a null xcc pb ++ equals null xcc, and somewhere here we will write for everything we do the assembler representation so that we know what we're doing here. Okay, so the next thing in our shellcode, what we need to take care of is the fact that in principle we could with this shellcode interrupt the execution of the thread at any time. In our particular scenario we won't do that. In our particular scenario we will we are setting the instruction pointer of a thread which has not yet been started, so we will not interrupt anything, and in principle we could assume that any parameters which might be passed to the thread are irrelevant. But good practice is to save all the registers such that we can later on resume without breaking anything. So save all registers integer, and the floating pointer, especially in like we are not modifying those, but we don't know what this load DLL will do, so we should just save everything. And asterisk code .pb++. You will use the 0x9c instruction. Which is called push F. It just pushes all the floating point thingies to the stack, and it also increments the stack position. And then what we also need to save are all the other registers, or the other integer registers, but with one exception. So what we will do here, we will use a loop xf to write some code for us, so that we don't need to like write the same code with a minor change 8 times and 16 times. Yeah, 16 times. So first we check if I is equals null x04. So the 04 register is the one we don't want to save. So if this is this, then continue. Keep saving RSP. We don't want to save RSP because RSP is the stack pointer, and if we then would restore it, that could cause trouble, since we are in the process of unwinding it from the stack. And then if e is more than 7, so if it's one of the newer registers, then we need to add a prefix, and the prefix is 31, and then byte, and then we want the instruction push is 50, and then to this, so let's see, push, for example, rax. So as you see, rax is 50, rbx is something else, but it's something close to 50. As you see, it's 53. And what we are basically doing here is we really just can count through the values with a certain limitation. So we use the logical OR to add I, and the I must be limited to 0 to 0x7. Let's go with this approach. I just want to make it look nice. So everything that is larger than 7 here gets this prefix, and so basically we have like two sets of 0x50 going from 0 to 7, and one of the sets has prefix, the other one is not prefix. The not prefixed one are the old registers, which are available in 32-bit mode as well. The prefixed one are the new registers introduced by AMD, which are used and available in the 64-bit mode. Okay, so you have written here a lot of code automatically, which is quite nice, since we didn't need to write it by hand. The alternative would be to have like here 8 lines of code, each of them handmade. So I think the loop is the more elegant approach. Good. Now what we need to do is we will need to increase the stack, so reserve some memory from the stack such that we will be able to use it for some temporary values. So let's see how we do that. We want a subtract from RSP 0x38 bytes. Assemble. RFP sub, not rub. Zack. Okay, so this is how it's supposed to look. Yeah. So asterisk code.pd++ is equals null x 38 ce ec 38 no 8348 should be right, looks right to me. And we write down what we did. Okay, next line. Now we will be preparing the arguments for our function call. So do we have enough time? Okay, I need to be faster. We are running out of time. So we want move rcx comma 0. As I said, the first one should be 0. Right, so address code punct pb plus plus is equals 0x c7 for 8 c7 for 8, yes, and here should be a dot. Then we need byte code punct pb is equal plus is equals 0 x c1 0x c1, and then we need a d with 0, so this is just a 0 argument. The next one is also 0, but it's our dx, dx, and it's almost the same, it just has here a 2. Okay, and the next one will be the address of the Unicode string. So we want to do there lat address r8 comma let's just write some dummy in here, p plus x77 bbccdd. There's something that gives us a recognizable pattern we can then recognize inside the actual instruction. So this was our layer. Yeah, I want this to be consistent with look. Wurscht. Let's not waste time. Right. So 8d for C 05 AD for C05, and now path offset plus base. We copy the thing. Just that this one we want R9. That would be D, I think. And we don't want path offset but module offset. Okay. Good. And now we need to load the address of our loader.dll thingy. No, we don't. We can call it directly. Then let's do it. Call that is shorter. 15ff and LDR offset plus base. Right. And at this point our injection is done, so now we need to undo what we did. So we undo that. Sub is add RSP38. So it, what is it? 48, 83. This is C4, and this doesn't change. Good. Okay, and now we, in the reverse order to our before approach, in the reverse order we will first do this and then do that, but not quite the same thing. It will be just a similar thing. So use the registers. So for int e is equals null xf e is greater equals 0, e minus minus. Again, if this then skip and prefix. If this then skip and if that then prefix, so this doesn't change. Prefix 41, and here actually I could have copied this line as well, we only need to alter it slightly. So we want to do this time pop, and pop is 58. 58, and then here this the reverse of that is 9D. Okay, so at this point we have unwound all the changes we did. The only thing remaining is to jump to the return address. JMP. Okay, FF25. JMP EP plus dummy value. Dummy value is always a dummy value. We are then always using the right correct offset point. PV plus plus is equals null x 25 FF and PQ no PD plus plus is equals ret offset plus base. And for good measure, let's add a byte at the end, null xcc, which we should never reach. In try. Right. We are almost done. One thing missing. We need to write this to the other process memory, because now we were assembling the code inside our own memory. So now we need to write it. Write process memory. Process, comma, andere code, comma, buffer my code, comma, size teaser of my code, comma, null. We don't care for the return value. Wait, this is not correct, I think. This cannot be correct. We need to get because this is like the address in our memory space. We need the address in the other process memory space. Bitte add the code. Byte address code. Okay, this is the base thing plus my entry minus my code. So we need to take the displacement of my entry and then add this to the base address in the other thing. Okay, that should be all. That should work. Hijack thread. Okay, let's run. Nope, we have some, oops. We have some error. We don't care for the warnings. Oh, yeah, the thing was still running. Okay, so debug, attach to process, attach, and continue. Okay, so we have first the breakpoint we already saw before, and now voila, bam, here we ended up in our own breakpoint. So where were we? Here. And then we have our push F, then we have our many pushes. This is the code generated by this loop. Then we have our subtract, then we have our move, and another move, and the two layers, and then we have our call, then we have our add to restore the stack pointer, and then we have a lot of pops to restore all the registers and our final thing. So let's put a breakpoint here before we return, and then let's go to the other main. Do we have a breakpoint there? Well, we have, but it's not yet triggered, so let's run. Okay, something failed. We broke something. Let's see why. We have 20 minutes, so that should be hopefully enough time to debug that. Okay, so let's see. I will put a breakpoint here. I think one of the arguments is wrong. Intermediate. Now let's go to memory. Or let's go here. So RCX, RCX, RDX. Okay, these are fine. R8. Wait, was that corrected? It's 8. Yeah, 8, 9. First comes 8, then comes 9. Okay. R8 is something, and let's see. This cannot do that. That's annoying. Let's go there. That is annoying. U short. Unsigned short. Wait, let's disable hex view. 16. 16 doesn't sound right. 16 does not sound right at all. I think the bug is somewhere there, but I'm not sure why. Because did we did it correctly? Load layer and address here. Path offset. Space. Path offset is 16. These look correct. This should be a alright, one bug already. That should be that 124. That sounds more reasonable. How long is this? They tell me 49. Yeah, that's 124. Since it's like Unicode, that should be fine. Okay, so this is okay. The next one should be this plus 2. It should be R8 plus 2. 520. That is fine as well. Plus 4 should be 0. Plus 6 should be 0. Plus 8. Plus 8 is void asterisk asterisk or Chartisten Wechar T Stern. That should be a pointer, but wait, that looks the thing is a pointer to a Wechar T Stern. Yeah, that makes sense. The path looks also correct. Why would that fail? Call stack. access violation reading location mine. Eight. What did we break here? Push sub. It looks valid. The first glance, it looks valid. Oh, I know what I screwed up. We need a NT path for that, not a we need an NT path and not a DOS path for this function. That will be it. That will be it. I think that will be the problem. We need to prefix this. What was that? Yeah, I think that's the right thing. Let's try again. Okay. Breakpoint here as well. Play. Right, let's test this. Okay, now we have the proper prefix for a DOS path. Okay, and it failed somewhere else. That is a mild success. We have a breakpoint here. We had a breakpoint here. Okay. Let's try again. Debug, attach to process. Attach. Zack. Okay, we want two breakpoints, one here and one there. Huh? We loaded the DLL. At least it didn't crash, but it didn't look like it loaded it because we should have ended up in this handle here. And then somehow our instruction is not correct. So intermediate actually looks correct. Let's see what happens. Okay. It is annoying that this does not work. have some offset calculation wrong. Return offset is this thing. Loader. Well, we have two issues. First of all, our DLL loading didn't work quite right. So with the right prefix, it at least didn't crash preparing it, but it didn't load the DLL. I'll just build it again, but it's fine. Let's see what it's complaining about. So we can debug, attach to process, attach to that, then continue, we are here, put a breakpoint there and there, continue, okay, output clear, continue. Now we go here to register, so that's the error code. Let's see. Just want to go to one of them. DLL not found. It doesn't like our path. Why doesn't it like our path? Our path was right, I believe. Intermediate. User Philip source. Reports hook test. x64 debug hacker DLL. That should be correct. Let's quickly inspect the first the Unicode and then the output handler. It should have usually worked. I'm not sure, we might have a typo somewhere, but on the first glance it looks all quite right. We start here and then just continue. Diallo DLL. Here it doesn't look like it also is resuming at the right offset, because I would expect it to jump directly up there. Okay, let's rerun it again. Okay, so here. Return value is 1. Okay, so we read that correctly. Let's write down this pointer. This is where we should resume. We can check in our own process. Now that is here. Okay, then it always wants to start at that offset, so that if that is correct, then it is correct. Right circle. Set context. Let's see what it tries. Let's see what it actually tries to load. Process name is test step x add. Okay, good. Let's run. We are here, right? Debug, attach to process. We are already attached. Play. Okay. And before we do again play, we will. Wait, it should have been. Is that recording now? No. Oh, it's recording to the right there. Filter correctly. Test. It's not test app, it's target app. Okay, let's now clear it. Then execute just this one line. Wait, see, that is not correct. The path is not correct. Why? Says copy, what says cut, what says cut. Here the path looks right, but it obviously tried to access the wrong path. Okay, I don't know why, but let's just go with it. Bug. Actually, we don't care for it. We can just try to just run it and see what it tried accessing. Create file. But now it didn't try to load it at all. I mean, that path would also not be correct. Something weird is in the past the code worked just fine without the prefix, so I'm not sure why now it would crash when it doesn't have it. Can try again. Clear, run. Okay, we don't want this breakpoint. Well, we are running out of time, and something is not working the way it should. I'm not sure why. Let me quickly test one thing. I will debug that code in a spare moment and upload the working version to Moodle. There must be some very trivial mistake somewhere. I'm just not seeing it at the moment. And if you have any questions, you can ask them by email as well. Yeah, so if you have any questions, you can ask them now, but since we are over time, I don't want to keep you any time longer. Yeah, so that was it for the current semester. As mentioned, there will be a part 2 and additional exercises during the next semester, so I would recommend to everyone to take a look on them and maybe take those courses as well. They will be also quite interesting, so the exercises will be much more hands-on, and the course, the low-level programming in C Part 2 will contain useful things about Windows API, about using the Qt framework to create graphical user interfaces, and with that you would be really able to create not just command line applications which do basic things, but do more advanced applications which do whatever you want. So I wish you good luck with your exams and the final project or other final projects if you have any. And I hope we will see each other in the next semester. Bye bye. Yes? Yes? So you will get a certain amount of points for the entire final project, and those points will be added together with the points from your homeworks, and based on that you will get a grade. But the criteria is the code must work and do what was asked in the description. You should have this unit test, so you test cases which are demonstrating that the code is working, and if the code works, then it's fine. Simplicity or elegance is not part of the grading. So as long as it works, it works. It doesn't have to be pretty. You're welcome. Then, bye bye.